Welcome back. Today we're going to take a look at a number of interesting applications of symbol tables and the binary search tree data structure to address problems with processing geometric data. So let's take a look at it. The idea is that we're going to be talking about geometric objects, not simple keys like strings and numbers. So here's an example. So say your geometric objects are points in the plane, and you specify a rectangle that's oriented with the horizontal vertical axes. And you might want to ask which points are inside the rectangle, or how many points are inside the rectangle. Or maybe what you're processing is rectangles. You have a set of rectangles, and we want to know which of these rectangles intersect, or how many rectangle intersections are there. These are interesting problems that have lots and lots of applications, from computer-aided design to games and movies, and also in abstractions such as databases and other situations where you might have multiple keys or multiple dimensions. And it's a very interesting extension of the ideas that we've looked at for symbol tables for all sorts of familiar applications. And surprisingly, binary search trees and the associated algorithms that we've looked at are going to provide very efficient solutions to a number of important problems in this area, and really have enabled new developments and new technology in all of these kinds of applications. So to get started, we're going to look at a simple problem called one-dimensional range search, and it really forms the basis for what we're going to do. It's a little bit of an extension of the ordered symbol table API that we gave before. And we're going to have the operations range search and range count. So one-dimensional just means we have one key. So we'll insert a key value pair as before. And what we want to do is be able to search for a key and the value associated with it. We want to be able to delete. But then we want these operations range search and range count. So find all the keys that are between two given keys, or give how many keys are there between two given keys. So for this example at right, we have insert a number of keys, and we're just showing them in sorted order. But then you might say, well, how many keys are there that are between G and K? In this case, there's just two. And then the client might say, well, what are those keys? You want to be able to return them. And this is a very common operation, say, in databases. You want to return how many taxpayers have salaries between 1 million and 10 million, and then which ones are there, and so forth. So range searching is a very important fundamental operation. Now, in geometric interpretation, we just think of the keys as points on a line. And so the key values, are just specified as points on a line. We might convert the letters to numbers, or keys might be numbers. And then what we're looking for is to find or count the points in a given interval in one dimension. So how we're going to implement that? Well, this is a basic problem that is very similar to our symbol table problem. We might consider keeping the things in an unordered array. Just put them in an array, and then, well, insertion is fast. We just add it to the end of the array. We might have to use resizing to make the array grow. But this is unattractive because for large numbers of keys, in order to count the keys that fall within a given range, you have to go through all the keys and test whether they're in the range or not, and to return them the same way. So take linear time for a large number of keys. If you keep the things in order, like in a binary search situation, then to insert, in order to keep it in order in an array, you might need to move the larger ones over one position and so forth. Our elementary implementation of binary search, when we did symbol tables, did this. So the insertion time might be linear, but then you can use binary search to look for the two endpoints. It's only going to take time proportional to log n, and then from that you could figure out how many keys there are, or return them all between the index of the lowest one in the range, index of the highest one in their range. So those elementary implementations are not acceptable for large numbers of keys because they have the linear time operations. So what we really want is to have time proportional to log n for insert and for counting. For range search, of course, we have to touch every key that we return, so the running time is going to be proportional to the number of keys that match. But anyway, those are reasonable goals, and they're easy to achieve. So, for example, what about one-dimensional range counting? Well, what we're going to do is just keep the keys in a binary search tree. And we looked at the implementation of the rank function for binary search trees, where for every key we can compute how many keys are there that are strictly less than that key. So in this case, the rank of E is 2 and H is 3 and so forth. So in a binary search tree, those rank numbers go in increasing order as we do an in-order traversal. And that's easy to compute. Either keep that rank tree as a field or keep a field which has the size of the tree, and it's easy to compute the rank from that. So how many keys between, say, E and S? Well, 1, 2, 3, 4, 5. It's actually just the difference between the ranks plus 1 if the high entry in the range query is in the table and not plus 1 everywhere. So there's the same number of keys between E and S as there are between E and T. 5. Between F and T, there's only 4. So that's a really 1D range count is a very easy computation to perform in log time with a binary search tree. The number of nodes examined when we do a search is the length of the search path to low plus the length of the search path to high to find their ranks, and that's going to be time proportional to log n. So in range search, well, we just do a recursive search, and to find all the keys between low and high, you look in the left subtree if any of them could fall in the range. You look at the current node, and you look in the right subtree if any of them could fall in the range. And it's easy to tell whether any of them could fall in the range by just checking whether the range overlaps the root or not. So if we're looking for all the keys between F and T, then we have to look at both subtrees of the root S, but we don't have to look at the left subtree of E because all of those are less than E and therefore are less than F, so we don't have to look there. But otherwise, it's a simple modification of recursive tree search to find all the keys. And it's easy to see that the running time of that is going to be proportional to the number of keys returned plus log n. So that's one-dimensional range search using binary search trees.